Hello and welcome to the live webcast of our 39th Electron mission called Baby Come Back. It is now 1:07 on the 18th of July, New Zealand Standard Time, and we are at T-minus 18 minutes to today's Electron launch. I'm Imogen Ray.
And I'm James Rattray, and we're here at Rocket Lab's Mission Control Centre to guide you through today's journey to space, a rideshare mission for 3 customers from Pad B at Launch Complex 1.
You might have noticed the red paint scheme on Electron today. That's right, on top of the primary mission to deploy customers' satellites to orbit, we will attempt to recover Electron's booster from the ocean after it returns to Earth under a parachute. Launch preparations are going well and Electron is vertical and ready on Pad B. We are scheduled to launch today at 13:27 local time or 1:27 UTC. For those watching in the US, that is 21:27 Eastern or 18:27 Pacific. We have multiple backup opportunities throughout the remainder of this 2-week window in case we're unable to launch today. Those launch timings remain the same for every day of the window should we need to reschedule for any reason. The good news, though, is that all operations are currently running smoothly and we're continuing the pre-launch procedures as we approach T0. We've got a ton of information to share about today's mission, so let's get started.
Absolutely. Baby Come Back will launch a total of 7 satellites to a sun-synchronous orbit for 3 customers. Riding on today's mission is a spacecraft for Spaceflight Laboratories, 4 CubeSats for NASA, and 2 satellites for Spire Global. Let's get into a bit more detail about these payloads in order of deployment. First off the payload plate will be the 4 CubeSats from NASA as part of the agency's Starlink mission, designed to test technologies to enable future swarm missions. Spacecraft swarms refer to multiple spacecraft autonomously coordinating their activities on orbit as one. Here's more from NASA.
Groups of self-coordinating spacecraft, also known as swarms, will open the door to exciting new opportunities in science and space exploration. NASA's Starlink mission is a key test of the technologies that will make this vision possible. Starlink consists of 4 identical small satellites. With Starlink, the goal is for a swarm to cooperate and work as one, with minimal human intervention. From Earth orbit, automated decision-making systems take the place of ground controllers, performing tasks from determining the relative positions of the spacecraft to planning and executing maneuvers. These types of operations are impractical to manage from Earth when a group of spacecraft is large or when a swarm is so distant the time delay for communications is significant. The mission also has an experiment that monitors Earth's upper atmosphere, with the onboard systems autonomously choosing which spacecraft is best positioned to make observations. Starlink's technologies will help realize a future where groups of spacecraft are able to work together on their own, whether close to home or far away.
And joining NASA's Starlink spacecraft are a pair of satellites for Spire Global. Spire's 2 3U satellites are carrying Global Navigation Satellite System radio occultation payloads to replenish its fully deployed constellation of more than 100 multipurpose satellites. Spire's satellites observe the Earth in real time using radio frequency technology. The data acquired by their GNSS-RO payloads provide global weather intelligence that can be assimilated into weather models to improve the accuracy of forecasts. Spire is the largest producer of GNSS-RO weather data, collecting over 20,000 radio occultation profiles every single day. Fun fact, Spire satellites flew on our very first commercial Electron launch to orbit all the way back in 2018 on the still testing mission. So it's great to have Spire back on board Electron today, all these years later. Let's learn a little bit more about radio occultation from Spire.
Severe and unpredictable weather patterns are altering the way we live and do business. To adapt to a rapidly changing climate, we need better weather forecasts. Enter radio occultation, an elegant technique that harnesses the law of atmospheric refraction. Spire's constellation of low Earth orbit satellites constantly gathers GPS radio signals as they pass through, decelerate, and bend in the denser medium of the Earth's atmosphere. We simply register the time delay of slowed signals to calculate the bend amount and reveal atmospheric temperature, humidity, and pressure. Spire has mastered a new paradigm of incorporating radio occultation data into weather models, massively enhancing the accuracy of forecasts at a relatively low cost will help us better track extreme weather. Ships and airlines can optimize their routes, saving energy, reducing carbon emissions, while farmers can maximize crop yields. Spire is a pioneer in this weather forecasting revolution, powered by radio occultation, where the laws of nature bend signals and guide us forward.
Now, putting our vertical integration philosophy into action today, both NASA and Spire are using our in-house designed and built Maxwell satellite dispensers to deploy their payloads from Electron's kick stage on today's mission.
Finally, we have the LEO 3 demonstration microsatellite built by Spaceflight Laboratory for Telesat. The LEO 3 satellite will provide continuity for customer and vendor testing campaigns following the decommissioning of Telesat's Phase 1 LEO satellite. Once deployed to orbit, LEO 3 will operate under an existing ITU network filing for Telesat's Lightspeed, the company's enterprise LEO constellation.
We're looking forward to hearing more about our customers achieving their science missions over the next few months. But for now, let's check in on the clock as we are at T-minus 12 minutes and 19 seconds, which means it's time to listen in to our launch director for the final go, no-go poll as we proceed through the final minutes of the countdown. Each operator will now check in from their stations to confirm all systems are go for launch.
All operators, this is the LD on mission, proceeding with the go, no-go sequence. Stage.
Stages go.
Avionics.
Avionics is go.
GNC.
GNC is go.
Beacon.
Beacon is go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MET is go.
RF.
RF is go.
MM.
MM is go.
Recovery.
Recovery is go.
LD SUP.
LD SUP is go.
That completes the go, no-go sequence. We are T-minus 11 minutes, 21 seconds and counting. We are go for terminal count at T-minus 10 minutes. From this time, the 3-word hold procedure is in effect.
Good
GC,
comms there
LD
from
mission.
Launch Director Joseph
GC.
Carpico and the team in Mission Control, confirming that we'll be proceeding with the rest of today's countdown and moving forward to liftoff in approximately 10 minutes and 45 seconds.
LD GC on mission.
Go ahead, GC.
Stage 1 igniter pressures verified, hydraulic pressures verified.
Roger, thank you, sir.
As always, today's primary mission is deploying our customers' satellites to orbit. But as we hinted at before, we're also very excited to have a secondary objective today, to recover Electron's first stage as part of our reusability program. After completing multiple marine recoveries and perfecting the process, we are going all in on this method, which involves gently splashing Electron down in the ocean under a parachute and then extracting it onto our recovery vessel for transport to our factory for refurbishment and eventual reflight.
The Electron vehicle today features new innovations developed as a result of the lessons learned on previous recovery missions. This one features improved sealing solutions within the interstage and power pack, and some internal components on the first stage Rutherford have been adapted for improved saltwater resilience. If you keep a close eye on stage separation about 2.5 minutes into flight, you should be able to catch a glimpse of the sealing as the first and second stages separate, revealing the inside of the interstage.
Let's hear a little bit more about the progress our recovery team has made on making Electron the world's first reusable small launch vehicle.
So with the rocket you can see behind me, it's red for recovery. We've developed from going from aerial capture and we've recently pivoted to marine retrieval. This gave us a few extra challenges, but with the engineers that we have at Rocket Lab, we were able to introduce some simple sealing solutions which will enable reusability. Over the last year, we've been working pretty hard in the background to requalify, assess, inspect the hardware from previous returned rockets. And my confidence level in relaunch is 100%. I wouldn't be doing this if I didn't believe in the program and what we're about to do. We're in a very fortunate position to have hardware that is easy to be dispositioned for reuse, and we can do this on multiple cycles. We've been working in the background with our engineers who initially designed the Electron to come up with life cycles, a refurbishment plan, and its eventual reuse. So it's very exciting, and it's going to be a great way for the company in the future. We're always evolving. Like anything, recovery has evolved. So the team has adapted awesomely. We've come up with new solutions to get the vehicle back to the factory for refurbishment in a state that we can actually eventually relaunch it. So it's been great progress from all teams involved, including the engineers who have been involved in the marine retrieval and also the redesign of the Electron vehicle. The whole program is being developed over a series of rockets. We're introducing minor changes for Flight 39. 41 will have a few more. 45 will be our golden child, which is going to have all our sealing changes. And this is going to enable us to disposition the vehicle accurately for reuse and create that historic information that we need to be able to disposition the vehicle for its life cycles and eventually turn the whole production into more of a fleet management style production, and overall putting the company in a better position to launch more frequent.
For today's marine retrieval, we'll be following a similar process to our previous recovery attempts, using a capture apparatus that you can see there on your screen to lift Electron on board the recovery vessel. Here's what we can expect from today's recovery attempt.
Around 2.5 minutes after liftoff, Electron's first and second stages will separate as normal, and Electron's second stage will continue into orbit, where the kick stage will separate and deploy the satellites. Back on the first stage, though, with all 9 Rutherford engines shut down, a reaction control system will reorient the stage to place it on the correct angle of attack to enable it to survive the brutal re-entry environment, what we call the wall, during its descent back to Earth.
At around 7 minutes after liftoff, a drogue parachute will be deployed to increase drag and to stabilise the first stage as it descends. In the final kilometres of descent, a large main parachute will be deployed to further slow the stage and enable a controlled splashdown. Once the stage is aboard the recovery vessel, our team will then begin the flushing and preservation steps to remove salt water, prevent corrosion, and secure the stage for the return voyage to our production complex.
Today's mission is another major step forward in our plan to evolve Electron into a reusable rocket, and we're taking all of this experience into the development of our medium-lift rocket, Neutron, as well.
All right, it's now T-minus 5 minutes before liftoff, but before we get to that, let's take a quick look back at our most recent launch, one you might not have watched yet. Last month, we launched our first suborbital mission using HASTE, our Hypersonic Accelerator Suborbital Testbed Electron vehicle. This mission, called Scout's Arrow, lifted off from Launch Complex 2 and was a large-scale test in partnership with Leidos for the Mark TB program, which is designed to increase the speed of testing for commercially available hypersonic systems. Let's check out that launch. Scout's Arrow was our third mission from LC2 in Virginia this year, following our first 2 launches in January and then in March, demonstrating an impressive launch cadence from our team, as well as tremendous continued support from NASA Wallops and the Virginia Spaceport Authority.
At T-minus 3 minutes and 4 seconds away from launch, Electron remains in good health and the satellites inside the fairing are good to go. The weather is trending green and the path to orbit is looking clear from Launch Complex 1 at T0. Soon we'll hear the call that LOX top-off is complete on Electron, telling us that the rocket is fully fueled for launch. When the rocket has completed fueling, Electron's internal computers, take over the countdown to run the vehicle autonomously at T-minus 2 minutes. Of course, you know the drill. From T-minus 10 seconds, we'll hear the launch director, Joseph Carpico, count down the final seconds before Electron's 9 Rutherford engines ignite 3 seconds before liftoff.
We're going to hand over now to Mission Control to follow along for those final moments before liftoff.
The vehicle is on internal power.
LOX load is complete. System is in recirculation.
AFTS is green, enabled for flight.
Anti-geysering is disabled.
Stage 1 and Stage 2, press for flight.
High flow engine purge enabled.
T-minus 20 seconds and counting. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Liftoff.
Liftoff.
The vehicle has cleared the pad, safing launch pad.
Stage 1 propulsion nominal.
And that's liftoff. Our 39th Electron launch vehicle is in the sky for this mission and progressing well on its way to sun-synchronous orbit.
The first major milestone in flight is Max-Q, or maximum aerodynamic pressure. Just ahead of 1 minute 20 seconds, Electron will push through the highest amount of aerodynamic stress it experiences.
Approaching Max-Q. Cleared Max-Q.
And with word from Mission Control, we can confirm that Electron has successfully passed through Max-Q and is continuing on its southeastern trajectory off the coast of New Zealand. The first stage's Rutherford engines are firing nominally as we come up to the next series of events in the vehicle's launch profile, starting with main engine cutoff, or MECO.
Electron will go through a clean separation of the first and second stages before the single Rutherford engine on the second stage
Guidance
fires
nominal.
up and
Altitude
takes
is
the vehicle
28
satellites
kilometers,
the rest
speed
of the
is
way into orbit.
1,022
We should
meters
see
per
those
second.
actions on screen and hear the call-outs from mission control operators shortly.
Operation then marks the first step in today's
Stage one
recovery
propulsion
mission as
holding
well,
nominal.
as that
Stand by
first
for
stage
MECO in
reaches
roughly 30
apogee before
seconds.
making its journey back down to Earth.
"15 seconds to staging."
Entered burnout detect mode.
MECO confirmed.
Stage separation successful.
Guidance nominal. Altitude is 77 kilometers. Speed is 2,082 meters per second.
Stage 2 ignition confirmed.
And there we go. We have confirmed a successful transition from the first to second stages of Electron's flight, with MECO, stage separation and second stage engine start all nominal. You can now see the orange glow of the space-optimised Rutherford engine as it carries
Stage 2
on into
propulsion
space.
holding nominal.
The payload fairing, the protective shell at the top of Electron, protects the satellites, but since we've cleared the lower atmosphere, they don't need this protection anymore. Let's keep an eye out for when the payload fairing, and there it goes, to get rid of all that dead weight, and we've seen it just fall away.
We've got some time before the next milestone, so let's take a look at the booster returning to Earth on the left of your screen. Everything's looking good there. A couple of minutes ago, the engines shut down on that first stage, and after the booster reached apogee, the reaction control system kicked in to reorient itself to place it on an ideal angle of attack for re-entry.
During re-entry, Electron will reach around 8 times the speed of sound on its descent, and the air around Electron will heat up to 2,400 degrees Celsius, generating an extremely hot plasma that creates a red-orange glow around the business end of the stage.
That stage 1 booster is doing well on its way back to Earth, and stage 2 is making light work of its journey to orbit. You can see on the graphs there, stage 1 looks like just reached apogee and is starting its descent back to Earth, and stage 2 is well on its way. Electron's second stage moving at a speed of 11,000 kilometers an hour and just passing through 192 kilometers in altitude.
Guidance is nominal, 200 seconds remaining.
Back to the primary mission here, we're coming up to a milestone you'll see used only on Electron, the swap out of our batteries that our second stage Rutherford engine draws its energy from to run its electric pumps. The vehicle has run through the set of batteries we used for stage 2 ignition, so now we need to swap over to a fresh set to keep things going. We call this move the battery hot swap. We should hear that call come from mission control shortly, but keep an eye on your screen too, as you might just catch a glimpse of them falling away.
Hot swap successful.
And there goes the call for a successful battery hot swap. Listening out now for confirmation of the deployment of the drogue chute on stage 1. That'll bring the initial velocity of the booster down to about a third, from around Mach 1.4 to just Mach 0.5.
AFTS is safed.
Recovery vessel confirms drogue.
And we're just confirming that we have just heard from Mission Control over the nets that we have had a nominal drogue chute deploy. This will demonstrate a significant reduction in velocity for our first stage ahead of the deployment of our much larger main parachute, which will take Electron to a soft splashdown in the Pacific Ocean, where our recovery vessel is awaiting to scoop it out of the water and begin that desalting process.
Stage 2 propulsion holding nominal.
Guidance is in terminal. 20 seconds remaining.
Stage 1 main chute deployed. And confirmed on video.
And that's confirmation from the team in Mission Control. The Stage 1 main chute has deployed and the booster is on about a 7-minute journey back down to the water. Meanwhile, in space, where that Stage 2 is ferrying our customer spacecraft to their orbital destination, we're moving at a very brisk 28,000 kilometres an hour. And it looks like we've just had Stage 2 shutdown.
Stage 3 separation confirmed. Nominal transfer orbit achieved.
And with that nozzle cooling and confirmation from Mission Control, we've had a successful second engine cutoff and kick stage separation. Today's satellites are headed to a sun-synchronous orbit, but as we mentioned before, our kick stage is on an elliptical first pass. It needs propulsion to course correct and orient it in the right trajectory for payload deployment, and that's where the Curie engine comes in. The first payload deployment sequence is scheduled for around 30 minutes from now, with a second scheduled for about an hour after that at T+1 hour and 40 minutes.
We won't have live video of payload deployment for this mission, but we will continue to follow along and listen out for those final few calls from Mission Control, as well as animated views of the end of the mission to visualize what happens in space when they do deploy. Before we take a break, we might want to have a bit of a check-in on the recovery again. I'm not sure if we've got that camera available, but I'm told that the recovery crew are patiently waiting for booster splashdown in the ocean. And once that booster is in the water, the crew will use their capture apparatus to grab the stage from the ocean and bring it aboard. If we get that recovery vessel camera back, we'll bring it to you as long as we have. But for now, we'll take a little bit of a break and we'll come back to you in a few minutes with confirmation of booster splashdown. We'll be back with you shortly.
Confirm splashdown of stage 1.
For those of you just joining us there, we have had stage 1 splashdown in the Pacific Ocean. And you can see it on your screen just there. We're with the crew aboard the recovery vessel who will now be making their way to the splashdown location to collect their booster. As operations continue as normal, we will take a break again. And when we come back, we will share when the payloads are deployed. We'll be back with you at around T plus 46 minutes.
LDGC on range.
Q catalyst heater scheduled to enable.
Welcome back to the webcast of Rocket Lab's 39th Electron launch. We are now T plus 44 minutes into the Baby Come Back mission, with the first of 2 payload deployment sequences coming up shortly. Before that, though, let's recap on the mission so far.
Baby Come Back launched at the top of the window, lifting off the pad at Rocket Lab Launch Complex 1 at 1:27 New Zealand time or 01:27 UTC. Electron had a clean pass through Max-Q main engine cutoff, first and second stage separation, and then second engine cutoff, followed by final stage separation from the kick stage carrying today's satellites. While that happened, the first stage began its descent back down to Earth under a parachute and has since successfully splashed down in the ocean. And while we were on our break, you would have seen that recovery vessel approaching the splashdown booster.
The kick stage is now coming up on payload deployment shortly. First, the Curie engine will ignite to position the kick stage in a circular orbit ahead of its mark. Then the NASA Starling satellites will deploy one at a time, followed by the Spire satellites. The Curie engine will then ignite again, making an inclination shift ahead of the deployment of LEO 3 for SFL and Telesat. That second deployment sequence will be taking place in about an hour or so, and we'll update you as it happens. Meanwhile, we're listening out to Mission Control for confirmation of that first of 4 Curie engine burns.
Curie ignition confirmed.
And that's Mission Control reporting a successful Curie engine ignition. This burn will last for around 120 seconds before shutting off, shortly followed by the start of our payload deployment sequence.
Curie engine cutoff confirmed.
Apogee is 576 kilometers, perigee is 574 kilometers, and inclination is 99.45 degrees.
Fantastic news there from Mission Control. Curie has shut down at the expected altitude. We have about 25 to 30 seconds now until that first deployment for NASA.
Payload deployment confirmed for NASA Starling 1.
And the deployment sequence has begun with the first of 4 Starling satellites for NASA out of their deployer.
Payload deployment confirmed for NASA Starling 2.
That's number 2 out of their deployer. We have 2 more 6U CubeSats for NASA coming up, followed by the 2 3U CubeSats for Spire at 575 circular.
Payload deployment confirmed for NASA Starling 3.
Number 3 there for NASA, the 3rd Starling CubeSat out of its Maxwell deployer. 1 more to go for NASA, and then the 2 3U CubeSats for Spire.
Payload deployment confirmed for NASA Starling 4.
And that's all 4 NASA Starling CubeSats deployed. Now it's time to deploy the 2 Spire satellites, which should be in quick succession here any moment now.
Payload deployment confirmed for Spire 1.
Fantastic news there from Mission Control. Payload deployment confirmed for Spire 1. We have the last 3U CubeSat for Spire coming up shortly, and then we'll have another coast phase briefly, followed by the SFL deployment at about T plus 1 hour 45.
And payload deployment confirmed for Spire 2.
Excellent news again from Mission Control. Spire's 2 3U GN SSRO CubeSats have been successfully deployed from Electron's kick stage, which of course marks the end of our first of 2 deployment sequences.
The payload for SFL today is out a little further than the other satellites on the mission, so the Curie engine will reignite 2 more times to get to the proper orbit. This will be a bit of a long one. We will be back at about T plus 1 hour and 44 minutes to give the final updates.
Q reignition confirmed. Q engine cutoff confirmed.
Apogee is 1,002 kilometers, perigee is 999 kilometers, inclination is 99.45 degrees.
And once again, welcome back to the launch of Rocket Lab's Baby Come Back mission, rideshare mission, We are in the second of our 2 deployment phases after a successful ride to orbit. As you can see on the right of your screen there, our recovery vessel has successfully captured the Stage 1 booster after its descent back down to Earth under a parachute. 90 minutes or so into the mission, we were able to pull it up. The team are quickly working on those desalting procedures. The Curie engine has just reignited and shut down for the 3rd time, and it gets us into the perfect position for deploying the SFL LEO 3 satellite deployment coming up very shortly, so let's take a look.
And there it goes. Mission Control have confirmed the LEO 3 satellite. The final payload on this mission has successfully deployed to its new home in orbit. That completes the primary mission for today's 39th Electron launch. Our recovery team are out in the Pacific Ocean continuing to work through the capture of the lift of the return booster and transport back to our refurbishment facility. Today's launch continues another exciting year ahead for Rocket Lab and our customers and the communities that use their satellites for everything from Earth observation and climate change research to weather monitoring, maritime surveillance communications, and everything that keeps us more connected than ever. If any of what you've seen or heard today excites you and you want to find out how you can join our team, visit rocketlabusa.com.
We're going to end the broadcast now, but keep an eye on our social media for updates and to find more about that recovery portion of today's mission, of course. We'll leave you with the recovery vessel on our way out. Thank you so much for joining us, and we'll see you again in about 10 days. This is Rocket Lab Mission Control, signing off.